The main question from the lab is which one of those two hydrate chemicals that you were working with, that you and the other lab group that you were working with, which one of those is the one that you would want to use in your shipping of your super awesome sneakers that you made? Now, a lot of people went and jumped right away and said, well, we take a look at the sheet where it has the percent, where you're doing percent error calculation. Well, there's one that's 51% water, and the other one's supposed to be only 36% water. So a lot of people are just going like, oh, well, it's got to be the one with the higher percent. And as it turns out, it probably is the one that you're probably going to want to use, but you need to be kind of careful, because if you're just basing it off of percentages, what would happen if you had a compound that was really, really light? Like maybe it had like lithium and some other elements that are really, really light, and it was 50% water was the hydrate. Well, that might mean there's not much water then, because you're working with a light compound. The water's mass compared to it is about the same, 50-50. You might not have an ability to absorb a lot of water. So really, ideally, the best thing you can use to be able to figure out which would be the best hydrate to use is when you do the calculation to find out how many water molecules are attached. How many moles of water are going to attach to how many moles of your compound. That would be the most ideal thing to look at. So hopefully, when you're looking at doing a write-up for that, that's what you take into consideration. All right, any questions about that? Cool. Then the next thing that the post-lab talked about was error. What are some possible sources of error? So we did a percent error calculation, and remember we take the absolute value of that, so we don't have to worry about if it's negative or positive. That only tells you whether or not you overshot the measurement or you were under it. We really don't care too much about that part of it. We're just interested in how far away from the right answer were you. So what were some of the possibilities? It's a really big group, so hopefully you guys can come up with more possibilities than the group before you that was even larger. So that means you're more awesome than they are. So what were some of the possible things that you saw? What were some of the observations you had in the lab that could have thrown off your data and caused you to have a percent error that's bigger than just a small little amount?
Not getting the exact weight of your grams.
Not getting, also like it could be a problem with the balance. Is that what you're suggesting? Yeah, definitely. That's part of that's a particular type of error that we can run into every once in a while. That the balance is off by a little bit. Typically, then it's going to skew everybody's data one way, because we know that it's the actual balance that everybody was using threw off everybody's results. That's definitely a possibility. Anything else? Anything from the actual experiment when you were observing? Did you write down anything like, wow, I didn't see that was pretty cool, and write down what was happening? Oh man, you guys observed it very well.
Heating the substance for too long.
Heat it for too long, that's definitely one of the possibilities. That was mentioned later on. If you heat it up too long, you could get a chemical reaction to take place. It might start to decompose, or it might cause a reaction with the air, and so oxygen might get added, and that might end up causing your mass measurements to be off, most definitely. Anybody like hearing like snap, crackle, and pops coming from the one that's heating? Yeah, good. Good observation. Make sure you write that down. Sometimes you might, if you're looking at it really closely, what you're doing, you're driving off water, you're producing steam, and that steam can sometimes kind of shoot a couple of those crystals right out of the crucible or evaporating dish or whatever it is that you're heating that chemical in, could pop out. That was one of the things mentioned later on, like what if some of it splattered out? So that's a possibility, in particular with this lab. One lab group I saw, they were trying to like speed up the process, so they noticed that it was drying out really well from the sides, but the center was still, looked like it was pretty wet, especially that blue one, because you can see that it was drying out by the color change. So they took a glass stir rod and they stuck it down into the crucible, and they tried to push the materials over to the side. When they brought the glass rod out, guess what was stuck to it? Some of the crystals. Is that going to cause an error? Yeah, definitely. So those are the things you need to be watching for, and make sure you write that down as an observation. Oh, some of those crystals came off. Because how are you going to get them back in? Are you going to try to like wash them off with distilled water back in? Well, now you're going to have it wet again. You're going to like continue to heat it up. That might be the better way of going about it. But try to scrape it in. Yeah, who knows what's going to happen. So we got to always make sure that when you're doing the experiment, and you see anything that could be a possible source of error, make sure you got that accounted for and written down. All right, so the last part of the post-lab was how would those things affect your result? So there's just 5 examples. So let's take a look at those and try to figure those out. Because there's some people that were like really struggling, they're just kind of guessing, like, I don't know, soot might be, it might make it heavier, I don't know, it might make it lighter, it might make it more water, less water. They didn't know. So here's what I would do to figure this out. And this is tough. This is hard thinking that you have to try to do to kind of figure out what is happening in these situations. But what I like to do is I like to just throw numbers in and kind of think about it with numbers, because trying to like picture it with my mind sometimes doesn't work so well, but for some reason numbers work really well for me. So let's say, as just an example, just throwing out any random numbers, that I know that my sample was 100 grams. Because 100 grams is a nice number to work with. And I know that the percent of water is supposed to be 20%. So if I knew it's supposed to be 20%, and I have 100 grams of the hydrate, I know that I'm supposed to have 20 grams of water. So I'm going to use that number as kind of a basis to kind of think this through. The other thing you need to have kind of with a mental inventory is kind of like, how is it that we calculate that? What is it that I'm subtracting to get these different numbers? How did I get the mass of the compound? How did I get the mass of water that was lost? You know, all involved in some subtractions. So when I look at if there was some soot that was added onto the bottom of the crucible, that means that the crucible is going to be a little bit heavier than what it was when I started. So when we take that measurement of that crucible, we write that number down, and we kind of like set that as that's a permanent number, that it's not going to change. But in this case, because soot's been added to the bottom of it, we have changed its mass. Now how is that going to affect what happens? Well, when I go to do my final subtraction to figure out how much mass has been lost, because that's the water that's leaving, it's going to end up looking not quite right. It's going to be supposed to have 80 grams of that compound, but because there's a little bit extra, a couple more grams, like this might actually be like, it looks like there's 82 grams of the compound, because a couple of grams got stuck onto that container that the compound was in. So when I do my subtraction to figure out how much water I have, I'm going to end up with 18 grams of water when I'm supposed to have 20 grams of water. So that means I'm going to have less water. It's going to show up that I had less water than I was supposed to have because that darn Bunsen burner was malfunctioning and put some soot and dirty, nasty stuff on the bottom of my crucible. So that's how I kind of reason through it. I try to think about what kind of numbers would I be expecting to get and how would that affect it. So if I saw something splatter out, which is definitely possible in this lab, you definitely could have seen something splatter out, which is number 3 here. You need to be able to kind of figure that out. All right, so let's take a look at the next one. It's still hydrous. So I'm expecting 20 grams of water to be able to evaporate out of my hypothetical hydrate. I'm supposed to get 20 grams of water out, but if I don't get all 20 grams out, what if I only got 18 grams out? What's that going to look like? Same thing as the soot. 18 grams when I was supposed to get 20 grams. I'm going to think, I got less. It's actually going to come up, in my numbers, there's going to be less water than what it's supposed to be. So numbers 1 and number 2 are pretty much the same thing. Even though it's kind of weird. We're adding mass onto our crucible. Here we're just not getting rid of enough mass. Not enough is getting out of the crucible. Next one, number 3, the splatter part. This is one that definitely could have happened in our experiment. I saw a couple of people that had, they worked with an evaporating dish with a watch glass over the top. I could see a couple of little chunks kind of every once in a while shoot up, hit the top, and maybe a couple of them might have escaped. So in this case, what's going to happen is I'm going to lose a lot more mass. Not only will the water, all 20 grams of the water will be gone, but some of that compound is also going to be gone. So when I do my subtraction, I'm going to see that 20 grams of water gone, plus I'm going to see some more mass gone as well. So I might see, instead of 20 grams, it might look like 23 grams of water has left. So when I do my calculation then to get my percentage, it's going to look like there's more water. I actually have more water in my calculation than what I'm supposed to have. So that's going to affect it that way. Does that make sense? Cool. Next one, number 4. What if we had a different crucible? Somebody else had a crucible that was like a couple grams heavier than mine. How's that going to affect my data? Not at all. Shouldn't at all. Because you're going to subtract it. Their group is going to subtract their crucible's mass out. You're going to subtract your crucible's mass when you're trying to calculate how much compound there is, how much of that hydrate, and how much of that water has escaped. So that really shouldn't matter. But the last one here, heating to the point where you get a chemical reaction where sulfur dioxide escapes as a gas. What would you conclude from that one? That's pretty much similar to which one of those other four that's up there. Splatter, yeah. This is, you're going to have more mass leaving than what you want. You just want the water gone. Now you're having part of the compound itself. It was sulfate that is now decomposed into sulfur dioxide, and that mass is escaping. So you get the same result. Your water is going to seem like there's a lot more water leaving than really ended up leaving. Any questions about that? All right, so don't forget the hydrate lab is due by the end of the day today. If you turned it in already, great. No problems there. So, next what I want to do is talk about doing some percent composition. We'll do an example of percent composition. Then we'll do a example of empirical formula, molecular formula calculation. And then we'll do that little online quiz. So we got an example up here on the board. If you want to write this down, you certainly can. Find the percent composition of tourmaline. Look at that beast. That's good. That's nasty. 1 potassium, 3 calcium, 6 aluminum, some borate, silicate, hydroxide. I'm just kidding on that one. Not going to do that one. If you want to figure it out, by all means, you can write down the formula and try to figure it out on your own. Because I don't even know what it is, and I don't really want to calculate that one. Let's do something simple like magnesium nitrate. That one's a lot easier. Not as many elements. So what do we need in order to calculate a percent composition? We need masses off the periodic table. So we know the formula. We have the formula in this case. We know that it's magnesium, 1 atom of magnesium, and there's 2 nitrates attached to the magnesium. So we've got 2 nitrogens and 6 total oxygens. So we go to the periodic table just to get the masses. I just want to know the masses of just the element itself. So I'm going to write that down here. 24.31 grams per mole is magnesium's mass. These last two, hopefully you have memorized it already from our plane crash activity. Nitrogen's 14.01, oxygen 16. Now that's just the mass off the periodic table for those elements. What we need is to then figure out what's the mass of the whole entire compound, because percent composition is like any percent. It's the part out of the whole. So we need the mass of the whole compound. What's the molar mass of the whole entire compound? So to figure that out, we need to add up 24.31 and 14.01 times 2. And then we need to add 16 times 6. Add all those up, which comes to 148.33. Be careful you don't just add 1 magnesium, 1 nitrogen, 1 oxygen. That's a common mistake I've been seeing a lot of people making when they go to calculate the mass of the compound. It's the number of atoms present you have to account for too. So to get the percent composition, we're going to have 3 of them because we have 3 elements. We've got magnesium, nitrogen, and oxygen. So magnesium is 24.31 divided by 148.33. Of course, to get a percent, we multiply by 100. So you get 16.4%. Now, nitrogen's part is 28.02. where it's the part out of the whole. There's 2 nitrogens that made up the whole in our 148.33. So 28.02 divided by 148.33. Times it by 100 to make it a percent, it's 18.9. And our last one is our oxygen. Six oxygens would be 96 grams. 6 times 16, divide that by our whole of 148.33. Times it by 100. 64.7. If we were feeling pretty confident on our first 2 elements, we could probably just add up those 2 percentages, subtract it from 100, because we would know that that last one has to complete the adding up to 100%. So 64.7. Sometimes it's good to check. Any questions about a percent composition? This one should be pretty easy. Percent composition, I feel pretty confident that almost all of our chemistry students are going to do really well with that one. And that one's not too difficult to work with. All right. Our next example. Empirical formula. So we've got a problem here. We've got a question asking what's the empirical and molecular formula. So we've got kind of a twofer in this one question. We're told we have 12 grams of this chemical, and it's broken down by mass, not percent composition. That's a little bit different than what we've been working with. In the plane crash activity, we were given all percent compositions. And what's the first thing you have to do with percent? You have to do what to it? Change it into grams. Right? We assume we have 100 grams of that compound, then the percentages will be the exact same number, but with grams. In this case, we're skipping that part. We don't have to worry about percent. They didn't calculate the percent composition. They just went straight to grams. That's what we need. We need to have grams in order to be able to do a T-chart to get moles. Because really it's moles that's the ratio relationship. So that's why we take the percent and change it to grams so we can convert from grams to moles. This is already in grams, so we're kind of a step ahead, which is kind of convenient. So, since we already have grams of everything, if I added up 5.94 grams and 0.62 grams and 3.46 grams and 1.90 grams, I'm going to get my 12 grams. These are the parts out of the whole. So I just take those grams and I just convert them right away with T-charts into moles. So for carbon, I'm going to take 5.94, make my T-chart. And convert from grams to moles. So I'd be taking my 5.94 grams of carbon and I would divide it by the molar mass of carbon up here on the table. So 5.94 divided by 12.01, and I get 0.4946 moles. Hydrogen, I do the same thing. I start off with 0.62 grams. I get 0.6139. Do the same thing with nitrogen, 3.46 grams. This time it's nitrogen, so in my T-chart I put the mass for nitrogen. So I'm going to take 3.46 grams of nitrogen divided by 14.01, and I get 0.2470. And last is my oxygen. I take my 1.98 grams of oxygen. One mole of oxygen is 16 grams of oxygen. That comes to 0.12375. I kept 5 sig figs on that one instead of the other ones were all 4 because it was a 5 at the end. And when you round to 5, that's a big chunk of uncertainty there. So I kind of left that one. So there, I have numbers now. I've got moles, which are numbers, but those aren't very convenient to work with. So what do we do in order to get nice, hopefully round numbers? Divide by the smallest one. So we divide all of these by 0.12375. So we know for sure down here at the bottom, oxygen is going to be 1. Because any number divided by itself is 1. Nitrogen, that looks like that's going to be 2. This one, I'm not so sure about. Should be about 5, right? 12 times 5 is 60. Yeah, that comes out to 4.96, so that's really close to 5. And 0.4946. This comes out to 3.997, so we'll say that's 4. No fractions, so we don't have to do another step of multiplying by that denominator in order to get rid of those fraction numbers. So my empirical formula is, just write them right in order. C4H5N2O. Now we've accounted for just about everything in this problem except for this last little bit right here, this 194.2. What's up with that? What is that information going to be needed for? What would we call this C4H5N2O that we've figured out? Is that empirical formula? That's the empirical formula. The other part of the question up here that's kind of cut off is empirical and molecular formula. This is that mass of the compound. This is what its mass when you add up everything like you're going to do percent composition. You should get 194.2 grams. So what do we have to do to this to see? Is the empirical formula also the molecular formula? We just have to add this one up. 12.01 times 4, so my carbons add up to 48.04. 5 hydrogens, 1.01 times 5 is 5.05. 2 nitrogens would be 28.02. 14.01 times 2. And I just have 1 oxygen, so I'm just going to add 16 when I get all that added up. And I get 97.11 grams per mole. So this, as a compound, would have this mass. That's its molecular or molar mass. They're telling us it's supposed to be this. We're short. We're going to have to multiply that through. What number does it look like we're going to have to multiply by? That's almost 200. This is almost 100, so it looks like it's going to be about 2. So if you don't know for sure, if you can't look and see, make sure you take that number and divide it by your empirical mass formula. The number you get is what you're going to multiply by. If you don't get a nice whole number, you probably did something wrong in your empirical formula calculation. It should always come out to a whole number. So we multiply everything by 2, so this is our empirical formula. Our molecular formula would be C8H10 N4O2. Which I think is caffeine. Or chocolate. One of the two. All right, any questions about that? All right, fantastic. All right, then take out an electronic device. You should also have your calculator handy and maybe a piece of paper to work on. We're going to do a quiz. Now, some of the questions are really short, so you got to kind of take a look at the time that you have to work on it. Some of them will only be like maybe less than a minute, like 45 seconds or so, but some of the harder ones where you have to do a lot more calculating is going to take like maybe 3 minutes before you have to get an answer in. So kind of watch that carefully. You can work together as a team if you want to. So you want like 3 people, you want to like huddle around like one person's phone or one iPad. So you can do. What's that? Yeah, so you can come up with a team name.